Okay, guys, welcome back. We are going to start the third session talking about charged molecules. I told you that there are two classes for charged molecules, and those charged molecules that doesn't contain negative oxygen, and those that contain actually negative oxygen. So we're going to talk about those that actually have negative oxygen in their structure. So let's talk about the first very simple one, and also we're going to talk about Lewis structures that actually must go beyond covalent bonding, and there are two sets of different stories if we go beyond covalent bonding or beyond octet rule. One of them is called dative bonding. It's actually kind of covalent bonding, but it's not a fair share of electrons. Okay, so we're going to discuss about dative bonding today, and there's also called hyperactivation bonding. There's also another covalent bond, and also it's not fair in another viewpoint, and they're both not fair in one common aspect, and that's when your central atom actually reach octet state. So that's why we call beyond octet rule. Okay, central atom fifth octet, but still you have the same kind of complexity to go beyond octet for the central atom to actually satisfy other surrounding atoms. So let's start about NO2 minus. This is called the nitrous anion, and the nitrous anion NO2 minus has a nitrogen. And to go about surrounding atoms, anytime we have negative oxygen, we actually put the charge for the number of oxygen that has negative. Okay, so if we have two oxygens and one of them is negative oxygen, we put the negative charge, and this gives us the negative oxygen things that we're talking about. Oxygen is group 6, so this is like this, and the other oxygen, the negative oxygen, actually must have the configuration of foldering. Again, if you have negative charge, you move toward more single reactive electrons, and if you have positive charge, you move back towards less single reacting electrons. And that's the structure for negative oxygen. It's just like a fold ring, okay, with just one single reacting electron, because it has more electrons in its valence shell, 7 instead of 6. And one more thing very notable about negative oxygens is that because their behavior is like fullerenes, or my bad, for like halogens, group 7 elements, they are more hungry to make bonds. So the first thing you do, you take care of your negative oxygen first. So when you have negative oxygens, there are two things. First, put the number of oxygens with negative charge to make it the same charge as your molecule, and then you first take care of your negative oxygens, which is just like fullerenes or group 7 halogens, and they only need one bond. So that's my negative oxygen. I take care of that first, and then there is one oxygen left, so I do actually put my other oxygen here with two single reacting electrons. If I share this first pair and also the second pair, as I do the second pair, my oxygen would be satisfied with 8. My nitrogen has also been satisfied with 8. So I could then make bonds, a double bond between the nitrogen and oxygen, and a single bond between the nitrogen and the oxygen negative. Okay, that's the structure of NO2 minus. One lone pair, two surrounding atoms, 3, and that gives me the geometry of this sort. This geometry, let's just put it here. So trigonal planar, that's the framework, and a trigonal planar with one lone pair would give you a bent structure. Okay, so that's the structure that you get for NO2 minus, a bent structure. Again, you could also draw it in an ordered trigonal pattern. If I just do that, you could see that the position that is top corner is not going to occupy any atom. The lone pair is going to, again, it's not going to be on the corner, it's going to stick to the atom. So that's the bent geometry for NO2 minus. Let's go to yet another example with negative oxygen in it. And that's the structure of carbonate anion. Now, carbonate is very important. Carbonate, you could find it in many rocks, and that's the form that could sequester carbon from the carbon dioxide in the air. When Earth first formed in its early stages, the rocks tried to sequester carbon in the form of carbonate to actually, from the carbon dioxide, to actually build part of our planet, which are carbonates. Okay, so there's carbon. There is 3 oxygens two of them being negative oxygens. That's the ones that we're going to take care of first. Our negative oxygens have the configuration of group 7 halogens, and our normal oxygen has 2 lone pairs, 2 single reacting electrons. So the first two are our negative oxygens, just like halogens with one bond. They would feel satisfied. Okay, so if I share this and I share this, 2 single reacting electrons on my carbon, and I form one bond here, it would give my oxygen negatives actually their satisfaction through octet rule, because now they have 8 electrons around them. And now I have one oxygen left that I could actually draw here. And if I pair this electrons, now my oxygen has actually 7, and my carbon also has 7 electrons around it, so I have to pair up this other single reacting electrons to actually have 8 electrons, but not only around my carbon but also around my oxygen, so it's a double bond there. So 3 surrounding atoms, 0 lone pairs. It's again this trigonal planar geometry, this time with 0 lone pairs, so that's going to be the exact same geometry for carbonate molecule. It's a trigonal planar molecule, and we could draw it like here in a trigonal planar framework. Okay, that's this one. Let's now talk about yet another molecule, and that's okay. Let's talk about CO2, the carbon dioxide. That's the gas that we exhale. Let's talk about that. That's not going to be the one that actually has oxygen negative in it, but we have to discuss it because we have not discussed it so far. Okay, so it's one of those that we need to discuss right now. Carbon, oxygen, oxygen. Now the carbon has 4 single reacting electrons. Each of my oxygen has 2, so I could just share these 2 with these 2, so that my oxygen would feel satisfied. Here my carbon is still having 6 electrons, and this oxygen has not shared. So let's share these remaining 2 single reacting electrons with this oxygen. Oxygen will feel satisfied because it has 8. Now if you look at the carbon also has 8 electrons around it, so I could just say there's a double bond here, another double bond here, and 0 lone pairs around my central atom, 2 surrounding atoms with the 2 oxygens, and gave me 2 overall. And 2 overall is a linear geometry, so we could talk about a linear geometry of carbon dioxide. Okay, and that's this structure, okay, or this molecule with no lone pair, and the bonds are going to push further apart to actually make 180 degree partition for those electrons, because they repel one another. Electrons repel one another. That's the main case that we're going to these different beautiful geometries. Okay, so this is CO2 with the linear geometry. And now what I'm going to do is that I'm going to actually go to another molecule, the CO. CO, carbon monoxide, is a gas that is toxic. It's called a silent killer, because if you're in a room that contains carbon monoxide and you're going to sleep in that room, it's going to kill you silently with no pain. So this is carbon monoxide, and it's because it's going to go into your lungs and actually attach to your hemoglobin, and actually it's not going to go away once it's attached to the hemoglobin, so it's going to disturb its function of carrying oxygen to your lungs, and that's why it kills you. So carbon monoxide, we have a carbon and an oxygen. If we do share the 2 single reacting electrons on my carbon with the 2 single reacting electrons on the oxygen, we will have a double bond that would satisfy oxygen's octet, but my carbon is not octet. Okay, so here's what we call a dative bond, and I'm going to talk about dative bonds here in this session, and that's what I'm going to do. Okay, so let's talk about dative bonding. And when we talk about dative bonding, it's actually sort of interesting that dative bonding is responsible for when your central atom, and the central atom here is the one that actually we talked about it previously. Central atoms are those, we consider those that have more single reacting electrons. So my central atom is not filling octet. I'm going to donate these lone pair because carbon needs, here it has 6 electrons, 4 here and 2 single reacting electrons. It needs 2 more to make it to 8. So I'm going to donate a lone pair, it could be either this one or this one, to the carbon. And for that, my carbon has to pair up its 2 electrons to actually put up an empty space. Okay, so that's what's going to happen. And I'm going to have this sort of bond. Okay. My oxygen would be left with just 1 lone pair around it. My carbon also has 1 lone pair of the 2 single reacting electrons. It has paired now, and there is the dative bonding. Now my carbon feels 8 electrons around it. It's satisfied, but these 2 electrons are donated from oxygen. That's why we have an arrow. Always we have an arrow. The tail of the arrow is our donor, and the head of the arrow, or the tip of the arrow, is our acceptor through additive bonding. And additive bonding, it's a donation always to the carbon that actually, to any element that needs 2 oxygens. Most of the time, it's oxygen that needs, that's going to be the receptor, or needs that 2 electrons, and it's going to be the receptor of this lone pair. Okay, so that's the structure for carbon monoxide. Lewis structure for carbon monoxide. You can see it's diatomic, so it's linear. The only thing that could be inferred is that the bond between the CO is stronger than CO2. In CO2 you have double bonds, whereas in CO, or carbon monoxide, you have triple bond. So that's why it's more stronger kind of a bond. So let's talk about our next molecule is CO3. We talk about carbonate, we talk about carbon monoxide, carbon dioxide, and let's talk about SO2, sulfur dioxide. Sulfur dioxide and sulfur trioxide, we're going to talk about both of those, and these are the gases that are mostly found in the around the caldera of a volcano. Okay, so that's sulfur. This is oxygen. Actually, we have 2 oxygens. So these are the surrounding atoms. The first thing that I'm going to do is to share these single reacting electrons of my sulfur with one of my oxygens on the top. So I'm going to erase it, and it's going to satisfy both my sulfur and my oxygen. And this oxygen, pure oxygen on the outside, is actually crying out. Where am I going to go? How am I going to join it so you make a O2 molecule? There is only one choice for you, and that's to actually get one of these lone pairs on the sulfur, which is the central atom, and actually donate it to oxygen if it's going to actually pair up its single reacting electrons, making a empty orbital, to accept those. Okay, so what I'm going to do, I'm going to just donate these lone pair to an oxygen that has paired up its 2 single reacting electrons, making an empty space to actually accept that lone pair. How many lone pairs I have around my sulfur? Just 1. How many surrounding atoms I have? 2. It makes 3. So it's kind of a trigonal planar again. This kind of framework or geometry again. Okay, and if you have a 1 lone pair, it means your trigonal planar molecule just going to detach this one to give you a bent geometry. You could also draw this in the framework of a trigonal planar. Again, you notice that the lone pair isn't going to be at the corner. Okay, so that's the structure of SO2. How do we show SO3? Okay, for SO3, it's going to be the exact same steps. Now here, instead of just 2 oxygens, we have 3 oxygens. The first one, we just do the covalent bonding that satisfies these both, and now you have 2 oxygens instead of 1 crying outside to join in. Okay, so you have oxygen, oxygen, and this one you actually gave a dative bond to join in. The second one, sulfur, well, it has another lone pair, so it could donate to another oxygen to give you the structure of the Lewis structure of SO3. Again, you have 0 lone pair here, 3 surrounding atoms, and 3. So this time you have a perfect trigonal planar molecule, or this kind of geometry, and I have actually showed it here that molecule has this kind of sort of trigonal planar geometry. For the trigonal planar geometry, it's also important that we could also show this trigonal planar geometry in a plane form, planar form, if you do a circle, this is going to be useful, and we're going to talk about this on and on, over and over, when we talk about, so additive bond, one of them is just, that is the Lewis structure of SO3. The thing that's kind of asked me whether we have to do lone pairs around surrounding atoms. No, if you do it for your own understanding, that's fine, but there is no compulsory thing to do it. You don't have to. And for the central atom, that's a completely different story. If you do not put lone pairs for a central atom, you're not going to understand it, and you're not going to figure out the geometry. So the geometry of a trigonal planar could also be viewed from the side, and that's important. We're going to talk about this on and on as we move on. Let's do one another example of these molecules. So the next one that I'm going to do is the structure of SO4 double minus. Again, we have oxygen minuses. Okay. My bad. So if you have, oh my bad, let me just stop, redo it real quick here. Oxygen minus, oxygen minus, oxygen, oxygen. And the first rule for the oxygen minuses was to do oxygen minuses first and then move on to the other surrounding atoms, because other surrounding atoms, or the oxygen minuses are going to be the most active. Okay, so the sulfur has two single reacting electrons, and I could actually satisfy this single reacting electron with this one from here, oxygen negative. If I do so, it will satisfy my oxygen negative here. If I do the second one, it would not only satisfy my sulfur, but it will also satisfy my oxygen negative as well. So I could actually do these two oxygen negatives. This is these so far. My sulfur is satisfied, my oxygen negative here is satisfied, my oxygen negative here is also satisfied. And again, two oxygens trying outside. So it's simple. I'm going to donate a dative bond to this one. If it shares its two single reacting electrons and making a space for it, and I'm going to donate the other one to the other oxygen if it does the same thing as well. So I have no lone pair, because the two lone pairs that I previously has is now donated as dative bonds. And my bad, I just said no lone pair, but write down 2. So 0 lone pair plus 4 surrounding atoms gives you 4 tetrahedral geometry. That's the framework, the tetrahedral framework. And since we have no lone pair, it's going to be the exact same tetrahedral geometry for the molecule, for the SO4 double minus molecule as well. So I could go on and actually draw a pyramid and say, okay, my sulfur in the center, O minus, O minus, O dative, O dative. Again, you could notice that I don't have to do the lone pairs for the surrounding atoms. Okay, you only do the lone pairs for the central atom to figure out how many lone pairs and how many surrounding atoms you have on your central atom. That's the structure of sulfate. Sulfate is one of the onion of one of the strongest acids, the sulfuric acid, so to speak. We could also do the structure of SO3 double minus, and that's going to be very simple as well. This time we have 2 negative oxygens and one of the one oxygen actually. So O negative here, O negative here. Again, O negatives are group 7, so they'd only need one bond or one sharing of electron, one covalent bond to feel satisfied. Satisfied. Also my sulfur receiving its 2 bonds, it's going to be satisfied, and this oxygen remains crying. So I could just donate it through dative bonding, and you could see, okay, I have now 1 lone pair, 3 surrounding atoms, again 4 tetrahedral geometry, that's the framework, and I have this one, and I could, if I detach one on the top, it gives me a pyramidal geometry or a structure for my molecule. A pyramidal geometry means you have this sort of geometry. Okay, again, you could note that the lone pair is not on the corner and it's sticking to the central atom. So that's the structure of SO3 double minus. Okay, let's move on to another example, which is the ClO minus. I'm going to see if I could make this one. It's going to be a little bit more lengthy from our previous videos because these are any molecules that we're going to do. ClO minus. Okay, we call it hypochlorite, and hypochlorite is actually a molecule that has Cl as the central atom and O negative as the one. Okay, so if just share this one, I will get a structure. It's a diatomic molecule. Both chlorine and O negative has been satisfied, so it's also a linear molecule because it's diatomic. Okay, diatomics are always going to be linear. It's only the discussion of how far or how near they're going to be. The more bonds between them, they're going to be closer together, and it's harder to rip them off. ClO2 minus, it's called chlorite. Now I have one oxygen outside of it. I do the same exact thing. One bond O negative, satisfied, wants to actually host no more atoms. The molecule feels stable, but we have one oxygen crying outside. Okay, so that's the exact same story. Beyond the octet rule for the central chlorine, it's going to actually donate one of its lone pairs to actually make the oxygen come into the molecule, welcome the oxygen, and the oxygen has to pair again its two single reacting electrons to open up the whole an orbital, an empty space for the incoming or donating lone pairs. Okay, so again you have two lone pairs, one of them is gone, two surrounding atoms, four tetrahedral geometry, okay, or framework, my bad, and with two lone pairs. Let's go. Oh, tetrahedral geometry with two lone pairs. This is my tetrahedral geometry, one of them detached, the other one detached. It should give you a structure. Okay, that's the structure for ClO minus, ClO2 minus. And you could notice that, okay, this is my pyramidal framework, and you have one lone pair, not here sticking to the head, and the other one not in the top but sticking to the atom. Okay, so that's how the bent geometry is actually being found. Let's go to chlorate, ClO3 minus, and in that case you will have three oxygens. Okay, so you could see that it's exactly the same steps. O minus, satisfied, and no more choice. I have to do dative bonding to host this one, and another dative bonding to host also this one. And if I do so, you're going to get this sort of geometry, okay? And that's what you get. Now you have one lone pair, three surrounding atoms, again four, again a tetrahedral framework, and a tetrahedral framework, if you have a tetrahedral framework with one lone pair, it will give you have to detach one of these elements to actually make way for one lone pair, and that gave you a pyramidal geometry, just like this that you could see. So that's a pyramidal geometry. I could do the framework over here one more time real quick. Let's just get rid of this. And you could see you have three oxygens and one lone pair that actually sticks to the central atom. Okay, now you have to, if you're doing it on your notebook, you have to do the second step on a separate part of the paper, because I'm doing it in a real fast mode, so I'm doing it actually in a very clever way. So I do the exact geometry the first time I draw it, so that I could actually draw the framework around it once it's finished. Let's move on to ClO4 minus. That's called perchlorate. That's also an onion. So again, we have ClO negative. So again, the four oxygens that I have here, one of them is negative. I took care of the negative oxygen first, because that's the one that is more active. And as I do so, this is satisfied, this is also satisfied. The three, this one I'm going to delete because it's also a nice structure. And three of these oxygens are crying outside. All of them are going to pair their single reacting electrons and receive dative bonding each. Okay, second lone pair and third lone pair to a fourth oxygen, ClO4 minus. So you could see that this time again you have 0 lone pair for surrounding atoms, tetrahedral framework with no lone pair. This is going to be actual geometry, so it's going to be a tetrahedral framework with no lone pair. Okay, I'm going to actually wrap it up here, and we will talk about more structures later on.